Hey everyone, it's Presley at ActOutGames.com here, and today is Science Sunday, and we're going to keep talking about some basic physics concepts in part 2. So today we're going to be talking about free body diagrams. Last time we talked about how forces are really just pushes and pulls and how to think about the things around you as well as the forces acting on them. So this time we're going to be talking about a more structured way to think about those forces called free body diagrams. In order to understand free body diagrams, you're going to need to know a little bit about this thing called a vector. So vectors are just a way to represent something with a magnitude or strength and a direction. When talking about forces, it's really important to know how strong the force is, as well as the direction. So when talking about a push, you want to know how hard the push is and the direction that the thing is being pushed. A vector is just a line with an arrow at one end. The length of the line is how hard the push is being, and the arrow is pointing in the direction that the push is. So I can draw this vector of a force going to the right, and then I can draw another one going in the same direction, and you can see that the new force is about twice as big as the original. It doesn't matter that this one is 2 pounds and this one is 4, or if that one's 20 or this one's 40. It doesn't matter, it's just that we can tell that the new one is about twice as big as the other one. Second, you're going to need to know a little bit about adding vectors. It sounds a little bit hard when you first hear it, but really it's just drawing the vectors one at a time, and every new vector starts where the old one stops. It's a lot easier to see an example. So let's say I have these 3 vectors, one going up, one going to the right, and one going down. So to add these together, I'm going to start by drawing the first one the same length as the one that I previously drew. This is where the graph paper comes in handy. I made this one 4, so I'm going to make this one 4 as well. And then I draw the second at the arrow of the first. I made this one 3, so I'm going to go ahead and do 3. And then the last one, the same direction, starting at the arrow of the second one. And I made this one 3, so I'm going to make this one 3 as well. So now I have this little shape here, and to finish it off, all I do is I draw a line from the tip of the first vector to the arrow of the last vector. This will come in handy later, but for now, it's just really important to show you how easy it actually is. So now we can start looking at free body diagrams to demonstrate forces on an object. So we're going to use one of the examples we used last time, which is just a pencil sitting on a table and not moving. So let's start by drawing our free body diagram. So we're going to draw a rectangle. It's very important when you're doing a free body diagram, you don't want to draw a picture of the object, because all you really need is a simple representation of what the object is. People usually use squares or rectangles, and this little rectangle here represents the pencil, but it's not a drawing of the pencil. So let's start with gravity. So gravity here is going to be 3 blocks long. And then we're going to draw our normal force, and gravity is usually called force gravity, or Fg, so I'm going to write Fg to label gravity. Now we're going to do our normal force up here. So our normal force here is pointing up, and it is usually the table or the floor pushing up on the object so it doesn't just keep falling and falling and falling. And it is called force normal, or Fg, or Fn. So I'm going to label it with Fn. So there is a free body diagram representing a pencil sitting on a table and not moving. Now let's do the vector addition with our force normal and force gravity. So we're going to start by drawing our force gravity, which is 3 cubes long. And then we're going to do our force normal, which starts at the end of force gravity, which is also 3 cubes long. So now we're going to add our vectors starting at the beginning of gravity and at the end of force normal, and we see that we end up at the same place. So that means that there's no net force and the forces are balanced, so it's not accelerating or moving, and that's exactly what we want. So let's try a couple more examples. How about a car accelerating to the right? So here is our rectangle, which we start all of our full free body diagrams with. So now let's do force normal and force gravity. Our force gravity is going to be 3 cubes long. And our force normal is also going to be 3 cubes long. They are balanced because the car is not flying into space or plummeting into the ground and to the center of the Earth. That's not what's happening, so they're balanced, which means that it is not going up or down. Okay, so let's label these capital F, lowercase n, capital F, and lowercase g. So that's how we're going to label those. So now let's start with FA, or force applied, which is the road pushing the car forward as the wheels turn. And this is going to be 4 cubes long. So we're going to label this capital F, lowercase a. And now let's do a tiny bit of force friction, which is not going to be as long as force applied because they wouldn't be accelerating if the force applied wasn't longer. So we're just going to make a little tiny 2 cube wide force friction. And then we're going to label this capital F, lowercase f. I just like the looks of capital F, lowercase f. Okay. So here is our free body diagram of a car accelerating to the right. This is one of my favorite ones to do. I always like doing free body diagrams where I can just like make lines longer and compare them. So let's do our vector addition. So when you're doing vector addition, it does not matter which order you put them in. So we're just going to do them in a random order. Like, you don't have to just do force gravity, then force normal. We're going to go ahead and start with our force gravity, which is 1, 2, 3. And then we're going to do our force applied, which is 1, 2, 3, 4. And then let's do our force normal, which is 1, 2, 3. And then our force friction. And then to do our addition, we start at the beginning of our force gravity and at the end of our force friction, and we get this net force. So our net force here is going to the right, but not as much as the force applied because the force friction counterbalances it. So our net force is 2 squares to the right. So let's do our last really, really fun example. So we're going to be doing an airplane coming in for a landing. So let's start with our rectangle. And there. Okay, so let's start with our force gravity, which we will make 4. 1, 2, 3, 4. Okay, here we got our 4. There's our gravity, capital F, lowercase g. So now we're going to be doing our force lift. So our airplane is still in the air, so it does not have a force normal. We're going to be doing force lift, which is like Bernoulli's principle, and it's what frisbees, helicopters, planes use to lift off into the sky. We will talk about that more in a later video. So we will make our force lift, let's say 1, 2, 3. Okay, so now let's do our force applied to the right. 1, 2, 3, 4. Okay. So there's our force applied to the right, and then a small bit of force friction yet again, which we will do 1, 2. So now let's start by adding these together. This is my favorite part because I get to add them all together and it makes a cool looking shape. So let's start with force gravity, which is 1, 2, 3, 4 again. 1, 2, 3, 4. And now let's do our force applied. So we have 1, 2, 3, 4 on that one. 2, 3, 4. And now let's do our force lift. 1, 2, 3. And then let's do our tiny bit of force friction. 1, 2. And then let's add these together. And my favorite part about this one is our net force is actually diagonal. When none of our forces are actually diagonal, they're all up and down or left and right, but we end up with a net force that is diagonally to the right, which is the way that the plane is landing, and that is what we wanted. So yeah, these are really fun to do. So that's about it for free body diagrams. I hope you like them as much as I do. I love these. They're really, really, really fun to do. It's really fun to understand and like make a physical example of the forces acting on an object, as well as the applied forces when you add them all together. Like, I really love doing net forces. So I hope you enjoyed these as much as I do. So yeah, thank you for watching, and that's my bye!